Okay, hello everyone. Welcome to the inaugural video of the First Principles group. So, again, the sort of theme I want for this group is sort of twofold. On the one hand, I want to sort of increase the attention given to being careful, rigor, scientific evidence, but also illustrate the beauty of science and the beauty of mathematical, logical thinking. And one of the topics that I've been looking at recently that I think would make a good introduction to the group and set the tone in the atmosphere is one that's deeply related to differential geometry, which is one of the fields of math that I'm deeply immersed in. I'm taking a course on it currently. And it's the Foucault Pendulum. And I claim, and by the end of this video I'll have claimed, that you can essentially prove without using physics that the Earth is spherical and rotating for free. You get the rotating part for free. And so let's begin with some history. So Jean Léon Foucault was an 19th century French physicist. And he's known for several things, incidentally. He's known for the gyroscope, which is a very famous instrument that's used throughout physics and astronomy. He discovered eddy currents, and he made a measurement of the speed of light all the way back then. When he died in 1868. So that's a very nice early measurement. But my favorite contribution of his was the pendulum that's named after him. And what it did was it demonstrated the Earth's rotation. Now, again, I claim that you can do this and get the fact that the Earth is spherical along with rotating. So one way you can do this is by using differential geometry. And so one of the things I'd like to do in this video isn't just to give you some fun science, but to also give you a crash course in the type of mathematics that I deal with on a daily basis in my work. So the topic is differential geometry. So what in the world is differential geometry? Well, it's geometry. So eventually we'll want notions of length, area, angles, things like that. But it's a type of geometry in which you can do calculus. And that's what the differential means. Okay? So let's set this up. Let's actually set this up. So buckle your seatbelts. Could be a bumpy ride if you and math broke up in high school. But hopefully you'll be able to learn something, because I do want to explain this in a way that's accessible while still being precise and rigorous enough to get it right. No compromises, right? So if you have a set, and this set will typically we call it a manifold. It's some surface, some object, and often we think of it as being embedded in three-dimensional space. Okay, so for now I'll stick with two-dimensional surfaces. So it has some curvature, it curves around a little bit. And so the first thing you would want to do if you wanted to describe the points on this object is you would want to give it some coordinates. Okay, so the analogy here is a sphere. So spherical coordinates, we would use latitude and longitude. If you give me the latitude and longitude of your position, I can tell you exactly where you are on the sphere. I can tell you how far away from the North Pole. I can tell you how close you are to the equator. So the first thing we want to do is give some coordinates for our manifold, our object. Okay. So coordinates of a smooth manifold have a certain property. And that property is that if you take two nearby regions And you want to ask, okay, what happens when I go from one region to another? What happens to the coordinates that describe those two regions? And the answer is they should vary smoothly. Okay, so if you're on the Earth and you go to some nearby point, so you go, say, 10 miles east, your latitude or longitude shouldn't change by that much. Okay, if they jump discontinuously, then something's wrong. Okay, something's wrong with the coordinates that you've chosen near that point. Okay, so this is what defines a smooth manifold. Okay, so smooth manifold has coordinates. Okay, and again, this tells you where you are, and it also has property that those coordinates vary smoothly, or another way to say it is they vary in an analytic sense or a differentiable sense as you move across the surface. Okay? So usually we'll write these coordinates using a function. That function will take every point in three-dimensional space and it will express it in terms of those coordinates. Okay? So here's an example. So here's a sphere. Okay, this is a basic sphere in 3 dimensions. It has radius 1. And one way to describe a surface is just by specifying some geometric property of it. Okay, it has radius 1. Square has all of its angles 90 degrees. Interior angles 90 degrees. That's a square. Okay. But we can also write down a sphere using some coordinates. Okay, and I'll do this now. So here, just to show you what this looks like, what this process looks like. So I would write down 3 variables. So this is x, y, z. So these are your standard variables from Algebra 1. X and y, you can think of that as your Cartesian graph, and z is just a third axis. So if you've had Calc 3, you would know x, y, z are all just perpendicular directions in space. Okay, if I wanted to write down a sphere, I would have to choose functions of 2 variables such that they satisfy geometric properties on that sphere. Well, what coordinates could I choose such that the radius is equal to a constant? That's what a sphere is. It's assuming a radius is constant. Well, think about what this looks like. The radius, if you're unfamiliar with the radius of a sphere, the 2-dimensional radius of a sphere, let's say r squared, satisfies a relation in 3 dimensions. It's the Pythagorean theorem. So recall the Pythagorean theorem. A squared plus b squared equals c squared, or in 3 dimensions, x squared plus y squared plus z squared equals r squared. And if that radius equals 1, if it's a unit sphere, that's just equal to 1. Okay? So this is sort of the basic, every point on a sphere satisfies this relationship if it's centered at the origin. So the center of this sphere will be at the origin. What functions do you know from algebra or trigonometry that square add up to 1? Well, one of those functions, there's actually infinitely many ways to do this, by the way. There's infinitely many ways to attach coordinates to an object. But the ones we're going to want are the ones that correspond to latitude and longitude. Those are angles. What functions act on angles? And the answer is the trig functions. So cosine and sine. So here's how I'm going to write this. So I'm going to define 2 variables, u and v. You can call them theta and phi if you want. And they represent angles. Theta, or u in this case, is going to be the angle that goes around the North Pole. So that's our longitude. Whereas V is going to be sort of, I'm going to call it phi later. This is going to be latitude. And this is going to go from the XY plane up toward the North Pole or down toward the South Pole. Okay. So here's one of those functions. The second one, this whole thing first. The second one, I'll need to use sine instead of cosine. Go ahead and copy this and make it sine. This needs to be sine. So I claim this will make a sphere. Let's check. So x, I've already defined, is going to be, what is it? Cosine squared, or sorry, let's just write it down. Cosine of u times cosine of v, and that's squared, plus cosine. Now instead of cosine here, I'll put sine squared. Or sorry, let me see. I think this should actually be sine. Yeah, this one should say sine. This one should say cosine. Got that backwards. There we go. So this one should say sine of u here. Cosine. The last term will be sine of just v. Let's check that this actually does equal 1. If it does, it means every point, no matter what u and v I choose, this will be on the unit sphere. Let's check. So remember how to square something? You square each piece if it's being multiplied. Okay, so this is cosine squared times cosine squared. This one will be similar, but it will be sine of u instead of cosine. Put that down. And then this one's just sine squared v. Okay. Now, is that equal to 1? Well, let's see. Cosine squared of a variable plus sine squared of the same variable. Do you remember what that's equal to? Cosine squared plus sine squared, if it's of the same variable, is always equal to 1. So there's some trig review. So these two terms add up to just cosine squared v, because the coefficients of that add up to 1. So this is just cosine squared v plus sine squared v, which again, that is of the same variable. Cosine squared plus sine squared equals 1. We did it. We've shown that this is indeed a parametrization, is what it's called. It's a set of coordinates for the sphere. So in other words, this u and this v that I've defined in this way, that they're related to x, y, z in this way, will make a sphere. So let's see. That doesn't look like a sphere. There's a problem. Something else we have to define. We have to define what values u and v are allowed to take. And as you see over here, it actually is telling you what values they're taking. So it's important later. Longitude goes from 0 to 2 pi. It goes all the way around. Remember, I'm using radians. So if you remember from trigonometry, radians is always in units of pi. So you have like pi over 6 radians, or pi over 2, or 2 pi. 2 pi radians is 360 degrees. Okay, so that helps you convert between degrees and radians. Now, longitude goes from 0 to 2 pi. What about latitude? Well, latitude goes from the North Pole down to the South Pole. Okay, so that spans an interval of length pi. but I want it to start at 0 at the equator. So that means I want negative pi over 2. That's 90 degrees. And here I want positive pi over 2. Hopefully that will make a full sphere. And indeed it does. And that black speck there, that would be the North Pole. And this sphere is now defined with coordinates u and v. So from now on, I'll probably refer to u as theta. So let's now say this. To that line. So the angles are, we typically use Greek letters for angles. So this is the letter theta. And I'm going to, conventions change, but for simplicity, I'm going to use theta as the angle that goes around the North Pole. So that's going to be called longitude. And phi. Phi is another Greek letter. And this will be latitude. Latitude. Okay? And these coordinates live on the sphere. Okay? They're measured from the center, but they are coordinates that describe every point on the sphere. All you have to do is give me these 2 points, these 2 values, and I can tell you exactly where you are on this sphere. Okay? So that means these coordinates are intrinsic to the sphere based on this function that I've defined. Okay? Again, this process is called parametrization. All it is saying, I'm taking 3-dimensional space and I'm defining a surface. And I'm defining that surface with two intrinsic variables on that surface. Okay? So this is how modern math would talk about writing down equations for surfaces and other things, is they would do it based on each individual coordinate. Okay? Okay. So what's the next step in making a manifold smooth? Well, we already know something about this manifold. We already know something about it based on the way I've defined these coordinates. Now you have to think back to calculus. Cosine and sine are differentiable. Remember that? So if you have a function, its derivative tells you how steeply the function's growing at each point. And if your function's derivative exists everywhere, then the function is a smooth function. Okay, so this goes back to calculus. So this is good Calc 1 review. The derivative of sine is cosine. And the derivative of cosine is minus sine. So cosine and sine are sort of each other's derivatives. But what does that mean? That means this function that I've defined is a differentiable function. I can take derivatives of it. So that means this manifold that I've defined is a smooth manifold. Okay. Let's figure out what those derivatives are. Okay. So first, let's write this down. So we have our matrix here. We have x, y, and z, and these are already defined. They're just perpendicular. X and y and z are all perpendicular to each other. And then I have my function. So now I'm going to use theta and phi as variables here instead of u and v. But again, it doesn't matter what you call them. Okay. So the goal here is I want to differentiate this function that I've defined. And if you remember anything from calculus, especially Calc 3, what you'll remember is you can take derivatives with respect to different variables. Okay? You can take derivatives with respect to different variables. So for example, I could take this function, think of this as a function, And I could take a partial derivative, which means just with respect to a single variable. Let's say with respect to theta. I'm going to take a derivative of this with respect to theta. What does that do? Well, again, if you recall, you just differentiate wherever you see theta. If you don't see theta, the derivative is 0, right? Because this is constant with respect to theta. It doesn't depend on theta at all. If you differentiate a constant, you get 0. Okay? So, what's the derivative of cosine? Well, we already talked about that. It's minus sine. Sine with a minus. Oops. Here. What about the derivative of sine? It's cosine. And this derivative is 0. Okay? We can do it again. We can differentiate with respect to a different variable, the other one. What does the derivative with respect to the longitude look like? Well, the same thing. You just differentiate wherever you see the longitude angle. Or sorry, the latitude angle. Okay? So let's differentiate with respect to the latitude. What do we get? So cosine's derivative is, where are we at? Negative sine. Okay. Do it again. So I'll get a negative sine a second time. And then the derivative of sine is cosine. Okay, so we have the derivatives of this function that describes our sphere. Okay, you might notice something about this. If you remember anything from geometry, from Calc 3, you remember something called the dot product. Right? So what's the dot product? The dot product is a way to figure out if two vectors are perpendicular, or what the angle in between two vectors is. Okay, so if I have two vectors, let's say I have vectors x, y, so now this is a general vector, so let me give it a different name. A, B, C, and then another vector, say D, E, F. These can be any numbers. They're vectors in three-dimensional space. There's an operation called the dot product. And what does it do? It multiplies each coordinate that corresponds to the other coordinate. So A is the first coordinate of the first vector, and D is the first coordinate of the second one. So I multiply the two. Then I add what happens if I multiply the second two. Same with the last pair of those. That's called the dot product. And the dot product is equal to, well, I'll just say it, if these two vectors have unit length, that means they have length 1, this is equal to, in fact, the cosine of the angle between these two vectors. Okay? So the visual is, I have two vectors. They look like this. And I can imagine they have the same length. The angle between them is alpha. So this is V1, and this is V2. The dot product between those two vectors, again, if they have this length 1, unit size, is just the cosine of that angle. Okay? So think back to trigonometry. If alpha equals 0, which means the angle is just closed, the vectors lie on top of each other. Okay? So that would tell you the vectors are parallel. Now, what's cosine of pi over 2, or cosine of 90 degrees? Cosine of 90 is 0. So if the dot product is 0, then there's a right angle between the two vectors. The vectors are perpendicular if you get the dot product equaling 0. Okay? That's very important. What's the dot product between these two derivatives that we just found? Well, take a look. It's sine theta. Oops, let's copy this. Sine theta, cosine theta, sine of phi, cosine of phi. Two negatives cancel. I get two negatives. A negative times a negative is a positive. Here I only get one negative, so minus. And then look what it is. Sine, cosine, sine, cosine. The exact same thing. And then here I get 0 times cosine, which is no contribution. That's equal to 0. So these two vectors are perpendicular. That's funny. So it turns out these two vectors define tangent vectors. Okay, so now there's another notion that we need on smooth manifolds. That's the notion of tangent vectors. Okay. So the idea here is I have my smooth manifold. In this case, it's a sphere. And what I would like to do, I think this is the right one here. Oh, it's too big now. So let me just write this as r equals 1 and go back to these u's and v's. I had u and v defined earlier. There we go. So here's what you imagine. In differential geometry, we imagine that at each point on our manifold, so I might want to show the point as well. So there's a point. I imagine there's a plane stuck to that point. So imagine you had a basketball and you took a sticky note and you just stuck it onto your basketball at some point. But imagine that the sticky part was right in the middle at one little area. This area, or this region, is a tangent plane, but it defines a vector space. So you can have vectors living on this little plane. And we need to describe vectors as living in their own tangent spaces. One of the reasons why has to do with these objects that we've found here. So these objects are vectors, and they live on the sphere. They are vectors on the sphere themselves. So these vectors, which I can actually show this, these vectors are here. So this object is the tangent vector that we got from differentiating the function with respect to theta. And this is the vector we got from differentiating with respect to phi, latitude. And this is the point on the sphere that I have. The span of these two vectors, so all the ways you can add them together. You could add them, you could subtract them, you could add twice the first one to 3 times the second one. You could take any linear combination of them, and that will produce a vector on this tangent plane here. And when we view this tangent plane as its own vector space, it becomes what's called the tangent space. and there's a tangent space at every point on the manifold. Okay, so they all happen to be very similar because this is a sphere, but in general, the tangent space will change from point to point. And how does it change? It changes because these basis vectors change. So if you remember anything about linear algebra, so this is from linear algebra, every vector, E is a vector, you can write that vector as some sum of two vectors in your space, or if your space is three-dimensional, it'll be three vectors. In this case, we have a two-dimensional space. So we'll have two vectors, this one and this one, and their sum will describe all the possible vectors on our vector space. So that means there's some coefficients, u1, and this will be a number. It could be a function, but in general, it's a number. For a fixed vector, it's just a number. Times what? Times v1. v1 is some other vector plus a different number times the second vector. So that's from linear algebra. This is a two-dimensional space. Every vector can be decomposed, if you will, into two of these vectors. And in that basis is what's called, we would describe it by writing down a sort of column matrix. It looks like this. So in the basis v1, v2, the vector v has components u1 and u2. If I chose a different basis, if I picked two other different arrows as my basis, I would get different numbers. Okay, so for example, if let's say this were my tangent space, and I had an arrow that looked like that, okay, I could decompose that into two perpendicular directions if I wanted to. And so this vector sort of looks like it's the sum of these two. Okay? So if I added this one and added this one, it would make sort of a right triangle. Okay? But I could choose different basis vectors if I wanted. For example, instead of choosing those, I could choose basis vectors that looked like this. Now, I claim that these two vectors, if you take a certain linear combination of them, it will give you this one. Okay? That doesn't look like it's true, but it is. In fact, the theorem of linear algebra is, because this is a two-dimensional space, the maximum number of vectors that you can have that aren't parallel is 2. So some linear combination of these two vectors has to give me this one, because there's two of them, and I only have a two-dimensional space. I don't have any more room to add a third vector. I would have to add a third dimension in order to have these three vectors, and one of them would have to point in that third dimension in order for them to be linearly independent. Okay, so we can change the basis over which we express our vectors. Okay, and what will that do? It will change the components of that vector. Okay. Okay. So the question is, if we're on a manifold like this, how do we tell what's perpendicular on the manifold itself? Okay, and the answer is we use the next topic, which is a metric tensor. So I know that these two vectors that I've taken are perpendicular, but how big are they? Are they unit vectors? Do they have the same length as each other? Well, to find that, we would go back to that dot product that I talked about, and we would take the dot product of the vectors with respect to themselves. Okay, so here's the first tangent vector. This came from my longitude angle, theta. Let's calculate this. So it'll look exactly like this calculation, okay, but not quite. Some of these terms will change. So instead of sine cosine, I'll have sine cosine, and then the two angles theta and phi will switch places. Okay, so the first term, comparing this to this, instead of sine theta, I'm going to have let's see, the order of them is mixed up. So let's see. So sine theta, cosine phi, so these two terms go together. And then instead of cosine theta sine phi, I will have cosine of phi times sine of theta. Okay? The next one, and again, the signs will cancel. The next one will say something a little different. It will say cosine of theta, cosine of phi, plus cosine theta, cosine phi. Now, if you stare at that for a second, you'll realize these are squares of things, and they should be, because these two terms are exactly the same. And these two are exactly the same. So we're going to get squares of terms. So this is really just sine squared theta, cosine squared phi. So I can simplify this greatly. Here's this. It should be here. And here. Now, what's the only difference between this term and this term? Well, the answer is this has sine of theta, and these have cosines of theta. So it's the same term, except this should say cosine. All right, and now we use that great property. Sine squared plus cosine squared is 1. So what's the answer? It's 1 times cosine squared phi. So that is the size of this vector. So this vector actually changes its size as you go along lines of longitudes. If you go up a line of longitude, phi will change. Okay? So in other words, if I start here and I move up, this tangent space, the basis vectors that define it will change sign. That's why I've added this little term here to make the size of that direction unit length. If I didn't add that, look what would happen. Okay, so if I don't add that term, then if I go up a little bit, it starts to look skinnier, right? Go up even further, it looks even skinnier. So if you recall, what's cosine of pi over 2? 0. So the theta direction, which is this way, if I go all the way up to the North Pole, tangent space just disappears. That's not good. That means the coordinates that we've chosen don't describe the North Pole very well. But that's okay. That's a typical thing that happens in geometry where you sort of make a sacrifice. You say, okay, I'm going to choose these vectors because they are nice vectors on the coordinates, using the coordinates that I've defined. Okay, so if you buy the idea that the best coordinates to use change size as you go along your manifold, then those are the best coordinates to use for the moment. Now you can normalize them, but that will make other calculations possibly harder. Okay, so let's add that back just so this picture looks mostly nice. Okay, so this vector has size cosine squared phi. Can you guess how big the other vector will be? This is the vector we got from differentiating with respect to the latitude, phi. How big is this vector? Well, let's see. I'll get sine squareds here. And each of these terms will have a cosine squared and a sine squared. So that's 1. So I'll get sine squared. But then I have cosine squared. So you can check this, work this out yourself. This is equal to 1. The metric tensor is, you can think of it as a matrix. The metric tensor is a matrix that tells you something about the tangent vectors on your surface and how they change from point to point. So the typical variable we would use is g, okay? And we typically give it some indices. So we would write something like GUV. So U and V tell you which variable you're at. So for example, G11 would be theta direction. So that would be this one. Okay. So 1 here would stand for theta and 2 would stand for phi. So it's a matrix. So what does it look like as a matrix? Well, we just calculated it. It looks like this. So this here component would tell you what the size of the theta tangent vector is, and it's cosine squared of phi. This tells you how big the phi direction tangent vector is, and that is just 1. These off-diagonal elements tell you what the angle between those two vectors is. And we've calculated that. The angle between those two has to be a right angle. Their dot product is 0. These are perpendicular directions. So that means this is 0 and this is 0. This object can pretty much tell you everything you want to know about a surface. Okay? You can use this to calculate the lengths of curves. You can use this to calculate the angles between vectors. But the thing we'll want to use this for this presentation is very specific. We want to use this thing to define parallel transport. So parallel transport is the mathematical operation, if you will, transport. The mathematical operation that we need to do our science with for this presentation. And it's related to the Earth's rotation. So here's the idea. Let's imagine I'm on this surface here, and I pick some vector on that surface. So here's a vector. It's just an arrow, okay? It's an arrow. The arrow doesn't depend on coordinates. Its components in a basis will depend on coordinates, but the arrow is just an arrow, okay? So no coordinates needed to think about this. And then what I do, I pick any curve. I just pick a curve. So let me draw maybe in a different shade. Here's some funky curve that lives on this manifold. And what do? I take this vector and I move it along this manifold. If I could copy and paste this on this program, I would. It's literally a copy-paste job. You're sliding it along this curve. It's called parallel transport because the vector that I started with, I got by taking this and moving it in such a way that I don't turn the vector. Okay, the vector itself isn't going to turn, okay, relative to its starting point. Now, it turns out that's not quite true. I'm not going to turn the vector myself. But it turns out if the manifold that I'm on, the surface that I live on, is curved, then there will be a real turning of this arrow, this vector. And there's a very easy way to picture this to prove to yourself that curvature can cause such an effect. Start on a sphere, start on a point, and I'm going to define a path. And here's the path. I go 90 degrees along the equator, 90 degrees to the North Pole, and then 90 degrees back down. Okay? That's my process. Let's parallel transport a vector. Again, just using intuition. I'm just going to use intuition here. Okay? Intuitively, what happens? Well, here's my starting vector. So I just move it straight up to the North Pole. And the vector now looks like that. Okay? So now picture in your head what it would look like. It would be pointing sort of out in that direction. So away from the starting point. Now I move it down this line of longitude. Again, I don't change its direction. So think to yourself, it's pointing sort of away or into the page, if you will. It's pointing into the page. Okay? And then I parallel transport it backwards along this curve. I'll speed that up. And you should already see what's about to happen. My vector came back crooked by 90 degrees. But I didn't change its direction. Its direction was the same throughout this whole exercise. And in fact, it turned by exactly a right angle. Okay. This is exactly what you'd expect if there's curvature. If your manifold is not flat. Okay, now you might be able to predict where we're going from that. So here's a nice picture of what this looks like. This is the exact picture that I just drew. You move a vector vertically, and down, and then back, and it twists. Okay? The technical word here is precession. This is the physics word. Precession is when you have some axis and it twists for some reason. Okay? So for example, the Earth's rotation actually precesses. A top, if you spin a top, it starts spinning, but then the top part of the top actually starts spinning as well, right before it falls. When the axis that it's pointing up starts to sort of wobble, that's precession. Okay? So, what we want to do is we want to figure out mathematically what parallel transport looks like. Okay? So, here's the statement. Holding a vector's direction constant means its derivative along that curve is 0. Right? If I tell you that I'm going to do something, let's say in mathematically, and the result is nothing happened, then as a function, you would expect the derivative of that thing to be 0. Right? Derivative 0 means nothing happened. The direction was constant. Okay? But that presents somewhat of a problem. So let's review calculus briefly. Again, I will try to speed this up a little because I don't want this to be too long and mathematically hazardous. So if you recall from calculus, let's say I'm differentiating two functions, product of two functions. How do I do that? Well, if you've had Calc 1, the answer is the product rule. The product rule says you ignore 1, ignore f maybe, and differentiate g. Pick g's derivative. Just forget f was even there. And then you rewind and you ignore g and you differentiate f. Okay? That's called the product rule. Let's apply the product rule to these tangent vectors and see what happens. In particular, a vector in our manifold. So you can imagine, let's actually define our vector now. So this would be our vector. So here's an arrow, and this arrow, it exists. There's nothing funky about it, no coordinates needed, but I describe it using coordinates. So that means that arrow will have some components. So let's take the partial derivative of a vector, v, and I'll use an arrow to describe the whole vector as one thing. Well, the partial derivative of a vector, the vector can be written using components in exactly the way I described. So there's some coefficients. So there's, let me describe the coefficients as v. So there's v1, and then these are my tangent vectors. So one of my tangent vectors, I'll call it E. That's a common letter used for tangent vectors. Plus v2, e2. Now, and depending on how much math you've had, I'm going to change the notation here. This is a sum of two things. And I can write a sum using a notation that's very common in math, using what's called sigma notation. Okay, now it looks very, very intimidating, but I assure you it's not. All it says is take all the things that look like v times e and add them up. Okay, so there's a kth v component and there's a kth basis vector. K starts at 1 and goes to 2. That's all. This is just a shorthand for this notation. That's all. But now I can use the property that the derivative distributes over sums. Okay, derivative distributes. So what that means is I can just differentiate this whole expression inside, meaning I can differentiate each one of these pieces. I can differentiate this one and then this one. So I'll describe that by writing, hit the parentheses now, by writing derivative of this. And by the product rule, what is that? Well, first I differentiate v. The components of the vector get differentiated. Okay. But there's a second term, and the second term is the derivatives of the basis vectors themselves. Now, if you stare at that for a second, you might not realize that there's a big problem with this equation, and this is where a huge branch of math comes in, called the connection coefficients and the connection on a manifold, okay, and studying how connections work. So this object is a vector. It's a bunch of things added together, and they're expressed in these e's, just like this was, the basis vectors. That's good. But this term is not a vector. It is not a vector on our manifold, and the reason why is because of this. This will be a vector in space, but it will not be a vector tangent to our sphere, our space. Okay, so we have to figure out what in the world this is. Okay, and the answer is we take a projection, if you will. We project its component onto the sphere. Okay, so you can imagine if you had a vector sticking out of the sphere. So here's a point. Here's a vector that sticks way out of a sphere. Well, that vector is perpendicular, so it's not going to have any projection. Okay? But let's say I have a vector that looks like this. So it's sort of sticking out. I can figure out what its shadow is by looking at this vector here. So if you had a sun, imagine the sun was over here, and it was casting a shadow on this sphere of this arrow, then this shadow, if you will, would be the projection of this vector onto the sphere. And I only want to consider vectors that live in my sphere. I don't want to talk about vectors that don't live tangent to the sphere, okay? Because then they're just any old vector. Vectors that live tangent to the sphere describe curves in that sphere, or on the sphere. Okay? So this is an exercise. What you do is you write down, this is a partial derivative. So here's a homework exercise. This object, the partial derivative with respect to the ith coordinate of your j'th basis vector, that'll be something that lives on my surface. So that means I'm going to give it a name, and these are typically called gamma, capital gamma. It's another Greek letter. There's tons of Greek letters in differential geometry. If there wasn't, we couldn't do it. There's too many darn symbols to use anyways. IJ K times EK. I don't know what these gammas are, but I know that this object will live on my sphere. But we know this isn't tangent, so there's got to be a non-tangential component. There's got to be a perpendicular component. And I'll call that thing N for normal. Normal is another word for perpendicular. Okay? So what do? You take the dot product of this equation with EK. And I'm going to assume that that object has unit size. So this is dot equals EK dot EK, ordinary dot product, plus the dot product of this N vector, this normal vector. But what is that dot product? Well, this is tangent to the sphere, and this is perpendicular. So that's equal to 0. What's EK dotted with EK? Well, it's the size of the vector, technically. But what we could do, to shorten this a bit, what is the size of a vector? Size of a tangent vector is the matrix value there. Remember, the metric we got, this metric tensor, it's a matrix that tells us how big the tangent vectors are. So if these are tangent, if this E and this EJ and EK, if these are all tangent vectors, then this is just G sub K, perhaps. Okay, so I leave it as an exercise. These tangent vectors I can write as derivatives of what? Of the function that I defined. And that function that I defined is related to my metric. So an exercise, a homework exercise, is to figure this formula out. This formula here implies, this gamma is equal to, and this is the first formula that legitimately looks a little ugly, not quite. 1 over metric tensor's component, the kth one, times a big matrix. And this matrix, there's actually a couple of these matrices. So this is how I like to split it up. There's one matrix that looks like partial derivatives with respect to my metric, which is a matrix. It's not quite that. It's actually the symmetric part of that matrix. So if the matrix will end up being anti-symmetric, you just take its symmetric component. And the notation to do that is put parentheses here. I'll calculate this myself in real time when we do this. There's another piece, is minus 1/2 times half here times just the full-blown derivative of the metric with respect to that k variable. Okay. So here I would put g. Okay. So this is not the full-blown equation. This is the equation that you get if you wanted to simplify it a little bit and you have a diagonal metric, right? You don't have to choose tangent vectors which are perpendicular. You can choose other ones, in which case this won't be a diagonal matrix. It'll have these zeros will be something else, in which case you would need to do some modifying of this formula. But for our purposes, this is right. Okay. This allows me to fix this derivative. Remember, the whole point of these complicated symbols here, these are called the Christoffel symbols, is to fix this equation so that when I differentiate a vector, it lives in the manifold. It doesn't stick out of my surface. It lives in the surface. So this is the notation called the covariant derivative. Looks like this. Covariant derivative with respect to, now we can differentiate with respect to a curve, for example. How do we do that? We take the curve, so let's say the curve is c, and we take the derivative of c, so c prime, of my vector. Okay? And this is the covariant derivative of the vector along a different vector. In this case, the vector happens to be the tangent vector to a curve. And that's what we are really interested in for this application. Okay? So, parallel transport means what? It means that this quantity, if you start with some vector v, the parallel transported vector will be a function of time. Okay? Parallel transport means that's going to be equal to 0. And that is the fundamental equation that we are interested in for this presentation. Parallel transport means that this is 0. Okay? What would that look like in component form? Well, that would look like this. So again, we'll leave this as an exercise. The derivative of my vector with respect to some parameter t, in this case t can be time, is going to be equal to these coefficients, functions of the metric, times, now this will be what? This will be the kth component, so there'll be two equations on my surface, one for each value of k, times what? Times vk times the tangent vector I'm differentiating with respect to. And in this case, it's, in this case, this should actually say I, and this should say DC. So again, this is, I'm giving you this because this is equivalent to this. J of T, dt. And similarly, I'm going to take it and I'm going to sum them up. So I'm going to sum I and J, both going from 1 to 2. So there's technically 4 terms here. They all look the same. They're just different components of this matrix and different components of this vector. So this is the real equation we want, not technically this one. This is what we're going to use. Okay. Oh, very important. There's a minus sign. Very important. So what are our, so let's do an example of this, just to simplify it, on this object. So here's an example of a manifold. It's a flat plane, or a flat disk, if you will. So this plane is flat. It has 0 curvature. If the curvature is 0, that means these gammas, these gamma functions are all 0. Okay? They're all zeros. So for case 1, on a flat disk / plane, we'll take it to be a flat disk for obvious purposes, all the components of any parallelly transported vector at all are constant. Okay? If it's flat and you're using flat coordinates to describe it. Okay? So you can imagine there being an x-axis and a y-axis, or x-axis, y-axis. This is x, y standard axes from algebra. Any vector that you parallelly transport will stay the same. It will not change at all. Okay? So what does that tell me? That tells me that my vector is just whatever it was when I started. V at 0, time equals 0. So at t equals 0, I pick an arrow, and then the arrow is the same in each tangent space anywhere else. Okay? Now, let's think about that in terms of if the disk were spinning. What if the disk was spinning around? Well, that means something about the coordinates. That doesn't mean anything much about the surface itself. The surface is still a flat disk. But let's say that my curve was this, some circle. Okay? Now, if I chose just an ordinary rectangular coordinate system, nothing happens. We know that. Rectangular coordinates are flat, no connection coefficients, nothing happens. But let's imagine we were looking from the perspective of someone on this surface, specifically. Particularly someone who lived on this curve, and the disk was spinning around about this North Pole here. Well, that means that the reference frame of that person would be changing as you went around. So you can imagine that our person, our observer, is at this blue point here, and from their perspective, if the disk is spinning, then their tangent plane, their sense of what it means to be oriented forward, is going to change with it. Right? It's going to change with it. So this tangent plane is going to spin around. It turns out you can get this using polar coordinates. So if you recall, polar coordinates, the calculus thing, polar coordinates looks like this. It's another function. we've defined, the type of function we defined up here. It's very similar. But it's a different type of function. It's a function that doesn't select a submanifold, but it's a function that describes the entire manifold. Okay, so let's write it. So this would be a function for x and y, right? X being this way, y being this way. Or, sorry, x being this way, well, it doesn't matter which one you choose. But typically x is chosen here and y is chosen here. Okay. What would that look like? Well, it would look like this. R cosine of an angle, and I'm going to call that angle very suggestively theta, plus R sine of theta. This is called polar coordinates. And the lines in these coordinates are circles. So R equals a constant is a circle, and theta equals a constant is some line through the origin. Okay. In polar coordinates, I will just go ahead and do the calculation here. How would we get the tangent vectors? Answer, we differentiate, just as we did a while ago. So I will tell you the tangent vectors now. So the first tangent vector on this surface is the derivative of this with respect to r. Well, what is that? Well, dr by dr is the same as dx by dx. It's just 1. So this is one tangent vector. Okay. What about the other tangent vector, t2? Well, that's the derivative of our function with respect to theta. And as we already saw, the derivative of cosine is minus sine. Derivative of sine is, where is it? Cosine. So these would be our tangent vectors. Okay. How do those relate to the ordinary rectangular vectors that I'm using here? Well, you can see how they relate here. They spin around. Okay? They rotate. One way to figure that out is to say that let's say, I'll put a hat on it here. So this is the standard notation you'd use for the basis vectors for x and y. The basis vector for x would be some coefficients. Again, this is a vector. I can expand it in this basis. So it'll be some coefficients. Let's call it a and b of this vector plus another coefficient times this vector. Okay. What is the x vector? Well, one way to write it, which I think will make this a little easier, is you can write this vector, where am I at? Right here. You can write this vector as 1, 0. That means I'm 1 unit in the x direction and I have none in the y direction. Okay. So that's one way you could write this. Yeah. Similarly, I can do coefficients for the y direction. Y direction will look like this. It'll have some different coefficients, C and D. All right, so how can we figure out what those vectors are in relationship to these tangent vectors that I've defined? Okay, so the answer would be to solve a system of linear equations. Okay, we'd solve a system of linear equations, and I want to save that time and not go through that, but I want you to work that out yourself and solve the system and confirm that this tangent plane spins around. So I've set the problem up for you. Okay, we're going to do this in the other way the other direction in just a minute on the sphere. So you'll see what the calculation looks like. But I'm going to save time. I don't want this to be too much longer. All right. So what actually happens when I put an arrow on this circle and I let it spin around? Well, we know it's not going to spin around. But from the perspective of someone on the sphere, or sorry, on this disk, it's spinning around. When it's over here, their basis is going to look the same from their perspective. But it's going to be tilted with respect to this arrow. So it looks like this. So the arrow doesn't change, but from the perspective, the frame of reference of the person on this curve, as this disk spins around, this arrow is spinning, and it's spinning clockwise. And if you're paying attention, how much does it spin around once you've gone all the way around? Well, it spins around all the way, and the frame of reference does a 360. So once you get to 360, it's come back clockwise a full 360. So the answer is that the change in the angle, where's that symbol at? Here it is. I'll call it delta alpha, or maybe delta omega, is what I used to call it. This is the total change in the angle of my arrow in this frame of reference after 24 hours, after a full rotation, is minus 2 pi. It does a full 360 clockwise. The minus sign means clockwise. Okay. Okay. What about for a sphere? So this is much more difficult. This requires that you calculate these gammas here. Okay, it requires that you calculate these gammas. And the equation, I'll just go back here. What's the equation? The equation is this. This is the equation for what happens when I take a vector and I parallelly transport it along some curve. This is the vector equation that I'm going to write down. And what curve am I going to choose? I'm going to choose a latitude curve. So this curve has a constant fixed latitude. Okay? And what I'm going to do is I'm going to take this vector and I'm going to move it, holding it as straight as I can, around this curve, this latitude curve. Okay? Let's see what the equations look like. Well, first I need these gammas. Okay? So again, you can go use the definition. Here's the definition of these gammas in terms of G. You know the metric for a sphere. So what you do is you plug that in to this equation. And what do you get? So gamma 1 is a matrix. Okay? Think of it as a matrix where I and J tell you where you are. K is if there's one of them. And what are the values? The values for gamma 1 are, just looking for a matrix to copy here. Let's just copy the metric. The values for this metric, or sorry, this matrix are, so now you're going to have to remember another trig function, minus the tangent of phi. Minus the tangent of phi. And this matrix is symmetric, so I'll put the same thing here. There's a second one. There's two of them. There's one for each direction. There's a theta. This is in the theta direction. This is in the phi direction. Again, don't put too much stock into these numbers. They're simply coefficients that we need in order to describe what it means to be parallel on our surface. On a straight line, basically. This is actually 0. This term ends up being cosine times sine. And it's also of the latitude angle. Okay? So those are the gammas. So here's what we do. We plug that into this equation, okay? And we work that out in terms of the variable phi and this latitude curve. Now, what is the latitude curve? The latitude curve, check this. What is the line of latitude? It's just a curve with constant latitude. That's all it is. So the coefficients of Cj can just be written like this. Theta will vary. So you can say it varies with time. So you go around the curve. And then the phi direction, the latitude, is just a constant. So I could give it a name. Phi 0. These gammas will be evaluated at phi 0. So this is, pick your favorite latitude. This is latitude 30, latitude 60. The equator, that's latitude 0. The North Pole, we can approximate that one at least. Again, remember, the metric doesn't like the North Pole. Spherical polar coordinates doesn't work very well at the North Pole. But we can still use this. We can get close. We can take a limit if we want. So this is a latitude curve. What's its tangent vector? Well, its tangent vector, it's not its unit tangent, but its tangent vector is just 1, 0. Right? And that's, you should expect that. At every point, the tangent vector just points horizontally. Actually, it's this vector here. Okay. So what does that mean? That means it's going around only in the theta angle direction. It's not going up and down. It's only changing in longitude, not latitude. Okay. So what does that mean? That means when j here is equal to 2, there's no contribution. So that just means that this is really just a sum over I, and j has to equal 1. So that simplifies this quite a bit. Okay, so now I invite you to work this out. Actually, I think we could work this last one out here. Don't want this to be too much longer. So what is V1? Well, V1 is going to be gamma 1 times this. The gamma 1 matrix is here, right? And I only want to sum over values where you're in the first row. That's what that means, or first column, equivalently. There's only one contribution there. This is negative tangent. So what's the answer? The answer is I get negative tangent, and this is when you're in the second coordinate, so I equals 2. So this is going to be V2. So that's V1. What about V2? What's the equation for V2? Well, now K is 2. So I look at the second matrix here. And this second matrix, and yeah, this is just 1, so I don't even need this. Yeah. DC's 1 component is just 1, so I don't even need to write that. So it makes it a little simpler looking. I look at the second matrix, and the only contributing component is this one. Okay? Again, you can look these up if you want. These are the Christoffel symbols, as they're called, for the sphere in spherical polar coordinates. So here's what I get. I get minus this term. And which one was that? That was V1. That's the first component of this row. So I get V1. Okay? So what have we learned? We've learned that the derivative of my vector, its components mix. How does V1 change? It requires that you know V2. How does V2 change? It requires that you know V1. Okay? But this is a linear system. So now you would use the theory of differential equations to solve this. Okay? So this is a differential equation, and I'm going to write the equation somewhat suggestively as a matrix form. So my vector will look like this. Let's just copy this down here, and then just get rid of this row. Sorry, get rid of this column. Now let's do it from scratch. Matrix 2 vector bracket. So my vector my arrow that I'm parallelly transporting, it has some coordinates in the basis on the tangent space. And how do they change? They mix in this way. I can represent that as a matrix. I can represent it as this matrix. 0, tangent, minus cosine sine, 0, times my vector. Remember linear algebra, do this matrix multiplication. What you'll get is, for the first component, you'll get 0 V1 plus tangent times V2. That's what we have here. And for the second component, similarly, you do this term times this, plus 0 times V2. And that will give you this term. This is a matrix equation. The derivative of my vector Another way to write this is the derivative. Let's go up here and do it. Let's use arrow notation now. So we're looking at the whole equation as one thing. The derivative of the vector is equal to a matrix, which I'll call M, times my vector. That's the type of equation that I just generated. It's linear. M has constant coefficients because this phi has to be evaluated on the curve I'm interested in. And on the curve I'm interested in, the value of phi is constant. That's the advantage here. That's where we come to this conclusion. The conclusion is that this vector equation can be solved exactly because this matrix is a constant. If this matrix depended on the variable phi, no chance. But because it's a constant, the theory of differential equations tells me exactly how I can solve it. Okay? And I don't know if you've ever heard of this, but you can take the exponential, you can take functions of matrices. So I don't know if you know what e to the t is, e to the t function. Function you have from calculus. Okay? E to the t is a function, it's an exponential function. It's the type of function you hear about with the coronavirus. You know, it grows exponentially. The solution is that you put m here, and here you write what? You write v at 0, the initial vector. Okay? Now, how in the world would you actually figure out how to calculate this? It turns out this is actually non-trivial to do. The way you would solve this is you would figure out the eigenvalues and eigenfunctions, eigenvalues and eigenvectors of m. Okay? So that's part of the theory of linear algebra and differential equations. Okay? I won't work through that detail. However, I will show you the result. Here's the result if you work this out. Let's choose our vector. So what type of vector would be easy? It would be one that's sort of parallel to the curve initially, right? One that's just simple to write down. Okay, that vector could be this one. Which one is it? Up here. This vector. This vector is the tangential direction along the along a curve of constant latitude. So the longitude curve, longitude basis vector. Let's just pick it to be that one. So I'll call it the tangent vector t sub theta. So in other words, I have an arrow, and the arrow points in the longitudinal direction. So it points along a curve of constant latitude, okay? The around the North Pole direction. If that is the case, if that is the vector that we begin with, then the solution to this system of equations, if you normalize the vector, is, where is it? Here it is. Again, it's in this basis, in this funky basis that we've chosen. E of t is going to be our two components, and what are they? They happen to be, so there's another trig function, don't need to worry about it too much, secant of the latitude, okay? And then we have some trig functions here. What are those trig functions? Those trig functions are cosine of minus t times sine of the latitude. And what's the y or the phi component, the second component? It's the same thing, except instead of cosine, it's sine. Okay, hopefully you can see what's happening. You might not be able to. Cosine and sine together draws a circle. So here's what happens. It will spin around. Spinning around. But it does not come back in the same direction. It comes back crooked. Why? Because when t equals 2 pi, what does t equals 2 pi represent? T equals 2 pi represents going all the way around the sphere, one trip. Okay? What's the angle here? Well, the initial angle was 0, right? The initial angle was just, what was the initial angle? The initial angle that I chose was angle 0, just straight ahead. The new angle will not be that. Instead, the new angle turns out to be, where is it? Where's the symbol? Delta omega. So that this is the symbol for the change after 24 hours. It is not minus 2 pi. It's minus 2 pi times this factor. This is the equation that we were looking for. Again, I had to skip a lot of it because I don't want this to be forever. This is the equation we were looking for here. So, let's go back up. When we did the calculation on a flat disk, we got that in the frame of reference of someone on a spinning disk, a parallelly transported vector that starts off pointing, let's say eastward, which is what we've got here. This is the same picture, pointing eastward. That thing would do a negative 2 pi spin in one revolution. On a sphere, that is not the case. And the reason why is exactly this reason here. So not only is our reference frame spinning around, but it's spinning around a curved surface. So the fact that this tangent space, the reference frame, is rotating around as I spin this curve around, it's going to cause a rotation. But that rotation is not all the way around. Okay? That rotation is not all the way around. It comes back crooked by this factor of sine of the angle. Okay? So, you should now think to yourself, okay, this was nothing but pure geometry, and yet I now have a purely geometric difference between flat disks and spheres. It comes back crooked. So, here's a question. Let's say you wanted to ask yourself, is the Earth a flat spinning disk, or is the Earth a sphere? How would you figure that out? Well, if you could find a physical system that behaved like a vector that was being parallelly transported around a line of latitude, flat Earth makes a prediction. And that prediction is that that vector, after 24 hours, it will come back exactly in the direction it was in when it started. It will not precess at a rate faster than the revolution rate of the Earth. Spherical Earth makes a completely different prediction. After a full 24-hour revolution, it comes back crooked. It does not come back where it started. And it comes back crooked by this factor, sine of your latitude. So, what's the answer? Which is it? Well, that is exactly what this pendulum was built to do. So a typical pendulum is kind of a nasty physical system. If you've seen a double pendulum before, you know that. Pendulums are a little bit nasty and chaotic. But the idea of Bernard Léon Foucault was to take a pendulum that was massive and very long. So, let me fast forward this a bit. Yeah, so there's a Foucault pendulum. And as you can see, it is wobbling. It is, pendulums go back and forth, right? They oscillate. The oscillation rate of this thing is horrendously low compared to an average pendulum. And the string it's attached to is very long. Some of these are 100 feet, 200 feet. And this bob weighs, you could do some physical exercises with this bob. It's very heavy. Okay? Because of the weight of the bob at the bottom and the length of the wire, things like air friction, things like friction in the device, and the natural ellipsoidal oscillation of the pendulum are hampered, so that it precesses as constant of a rate as it oscillates at as constant of a rate as it can. Okay. This experiment has been done. It's being done all over the world as we speak. So there's Foucault pendulums all over the world. Okay, there's one at the California Academy of Sciences. There's one at Derby in England. There's one in India. There's one at the Musée des Arts in Paris, and there's even an experiment at the South Pole was carried out. There's an entire Wikipedia page called List of Foucault Pendulums, in fact. Let's just go there. This is all the Foucault pendulums that exist in the world. Here's all the ones in the United States. There's a ton of them. So pick your poison. Pick your favorite area. Pick your favorite science museum or university. You can go watch a Foucault pendulum oscillate. And it will precess. And it will precess at exactly this rate. What this demonstrates is that the Earth is rotating. But because of differential geometry, or at least one proof of it is due to differential geometry, the flat Earth prediction disagrees with the spherical Earth prediction. So which one wins? Well, you can guess which one wins. So here's a couple of facts. So if you're somewhere between, say, 30 and 90 degrees latitude, the vector will come back completely crooked. It will come back completely crooked. If you're at the equator, you get an even worse prediction from flat Earth. This completely destroys the flat Earth prediction. It doesn't precess at all. There's no turning of the axis of the pendulum. The pendulum will not turn at all. And the reason why is because the equator is a straight line. Now, that might sound like the craziest thing you've ever heard of, but it's straight on the manifold, on the sphere. Remember, curves have to live on the sphere. So what counts as straight is a local property, not a global one. On a flat piece of paper, a straight line is the only straight thing you can draw. But on a curved surface, curved lines can be straight because they're locally straight. Okay? If you were to get in your car and hold the steering wheel as tight as you can and then drive straight, you would drive along a geodesic, basically, is the idea. Or you can imagine an ant on the sphere, and it decided to walk in such a way that it did not deviate from where its eyes were looking. It would go along a straight line. These are called geodesics. Okay, a straight line's a geodesic. The equator is a geodesic, which is why there is no precession of a pendulum at the equator. So if you really want to destroy the flat Earth prediction, go to the equator. Okay, but you can prove it for any latitude line. So here's another one. Here's latitude equals, so let's do pi over 2 times, I think Knoxville's latitude is 35.9. I think that's the case. So that will show you how much it comes, 35, I need to divide that by 90, of course. This is the fraction, 35 degrees out of 90 degrees. If you do that in Knoxville, it will come back crooked by exactly the latitude. Okay? Now, you don't want to do the experiment at exactly 30 degrees latitude. Why? Because pendulums happen to be two-way vectors. So a pendulum spinning in this axis, so if a pendulum's oscillating this way, it looks the same if it's oscillating this way. Right? Because a pendulum goes back and forth. Okay? So a pendulum is more like an entire, it defines an axis rather than a vector. You can think of it like that. But it still will precess. So you can watch it, if you will. It'll come back a 180. It'll do a 180 spin. The most accurate place you can get the flat Earth prediction right is near the North Pole. I think I have to draw it like this. Yeah. So here's near the North Pole. This is right at the North Pole. And this vector will just spin around counterclockwise 360. Or sorry, clockwise 360. It's clockwise in the local frame of reference. And that's exactly what flat Earth would predict. But what if you went to negative 90 degrees? The South Pole. Which way does it turn then? Then it turns clockwise, counterclockwise. It turns the opposite direction at the South Pole. So that's easy. Go to Antarctica. Actually, this has been done. So that was one of the things it claimed had been done, is the experiment was carried out at the South Pole, where it was assumed that the rotation would have maximum effect. Okay? And so the pendulum had a length of 100 feet and a 50-pound bob at the end. And the researchers confirmed a 24-hour rotation rate of the oscillation plane of the pendulum. Okay? So if you're skeptical, don't just believe. This is one of the things that I want to emphasize in the group is science and mathematics are something you do, not something you're told. So if you want to see the flat Earth prediction be completely destroyed and see for real that the Earth is, in fact, a rotating sphere, just go to a Foucault pendulum somewhere in the Earth. There's dozens of them in America. There's more than dozens. There's hundreds. There's the list. Pick your poison. Okay? Go to a Foucault pendulum, record it, record what its angle is, its position at one time, and then come back 24 hours later. It will be crooked, and it should be crooked by exactly this formula. And the amazing thing is you can get this without knowing any physics except one fact, which is that a pendulum does behave like a parallelly transported vector. Remember, there's nothing affecting a pendulum except for gravity. Okay? And so once you have a pendulum and you know, okay, I set the pendulum off in motion, and nothing I really do to it's going to change its oscillation. It's just going to oscillate there. It's going to do its thing. If you minimize all the other forces acting on it, then it behaves as a vector that's being parallelly transported around a curve, around a latitude curve, based on the Earth's rotation. So if you're skeptical of the Earth's shape, test this out. Heck, build one yourself if you have the engineering knowledge. I would love to see an example of someone building their own Foucault pendulum and testing this formula, driving all over America and test this formula out. I don't know if you can build a tabletop Foucault pendulum, but in any case, they're here. So if you want to take the easy route and go to universities, I want to go to one very soon I want to go to this one in San Francisco. It's a short one with a super heavy bob at the end, a 100-kilogram bob, and it's a 30-foot. Incidentally, one of these has to be large, and the other one can be relaxed. That's typically the way these work. Although this one in Colorado, this one's just enormous. 130 feet, 166 kilos. That's a monstrous pendulum. Okay, some are much longer than that. I'm not sure what the longest one is. It's on this list. But yeah, in any case, go to one of these. I would love to go to one soon, probably this summer when I go back to California. And see it for yourself. See the effect and see which prediction it matches. Okay? Science is done by observation, not by being told what's true. Observation and this kind of critical analysis that I've done. I've skipped a lot of steps, of course, but this kind of analysis combined with real-world observations is what makes science so great. And so the flat earthers have one point, which is not just brushing it off, which is that they don't want to be told what's true. They want to see it for themselves. Well, here's one way to see that. Okay? And the beauty of it is that this didn't take any physics. This just took math and geometry. Okay? So that concludes this presentation. I hope you learned something. Hopefully you were able to at least pay a little bit of attention. So this is the Foucault Pendulum at COSI Columbus. So you might go see this one. So the fact that it's knocking over those balls indicates that it is in fact precessing. So that is really cool. And just as an aside, this same mathematics that describes differential geometry is the same math that describes space-time. It's the same math that describes meteorology and weather systems. Okay, so math is everywhere. And that's one of the reasons it's so beautiful, is the mathematics doesn't take away from the picture. Understanding it doesn't take anything away, it only adds to the beauty. Okay? All right, I will see you soon, and hopefully this group has some fun. See ya.